So just a brief overview of yesterday, should you remember. We started with Newton's third law, and then we mixed in the concept of impulse and developed conservation of momentum. Right, we did that at the end of class yesterday. And what we had derived was something that looked like this: the momentum for our objects after something happened was equal to the momentum of our objects before something happened. And I'm putting, some dots there trailing off because we base it on two objects, but you can have more than two objects interact at once. Or more importantly, your system can consist of lots of objects that are interacting at different times. Ultimately, what I'm saying to you is that the momentum of a system stays the same over time. Individual momentums may change, but the total momentum of a system stays the same over time. So any one object may gain momentum at the expense of something else losing momentum. And we're going to focus today on one-dimensional examples like we started yesterday. But this applies in 3 dimensions. So a 3-dimensional system will still conserve momentum. But since we want to do a little bit of the mathematics behind this, we're going to focus on one-dimensional examples. And we're going to focus on also discussing 3 primary types of collisions. So without any further introduction, let me set up a simple interaction. Let's stick with the cars. They were green and yellow, although they are certainly not green and yellow. We all know that. That's the joke. All right. So there's always going to be the consideration of states of a problem. And a collision generally is, and I'm saying generally, but I want you to kind of get this in your notes, these words. It is the instantaneous moment before contact and the instantaneous moment after contact. You may not understand why I'm saying it like that, but I need you to at least kind of get that into your notes, and then I'll say it again as to why. It's the instantaneous moment before contact and the instantaneous moment after contact. Now, the reason I'm saying, so let's talk about a typical collision. And in this particular collision, let's state that maybe I've put some Velcro on the 2 cars, and that during the course of the collision, the 2 cars are going to link up and move together. Does that make sense? I've got some examples of this we're going to see in our activity tomorrow. So let's start with this car, mass 1.5 kilograms, traveling this way at 2 meters per second, and this car, 0.5 kilograms, at rest. Okay? There will be a collision. The collision's in the middle. Afterwards, the cars link up and move off, I think, this way to the right, but I don't really know for sure until I do the problem. And I'd maybe like to know how fast are they going after the collision. Everybody see a collision occurring here, one object striking another. Is that pretty clear? I've set this problem up so that there's a clear before and a clear after. These problems are so straightforward to do. Identify the before and after. Identify what direction you will call positive. I do that in the middle. I just put an arrow and I indicate that that's the direction I'm going to call positive. Remember, vectors here. And then put an equal sign. You're going to have the momentum of the first object plus the momentum of the second object before the collision equal to the momentum of the first object plus the momentum of the second object after the collision. I'm not going to put a whole bunch of extra subscripts. I'm kind of laying my problem out directly beneath my picture to ensure that I'm kind of keeping track of what part of this is before and what part of this is after. Does that make sense? But if you want, you can put a little initial and final. It just starts to get kind of junky when you start doing that. Would you agree? Now remember, momentum is mass times velocity. So I take the mass and velocity that I know for every object and put it in for each of the momentums. So object number 1, mass 1.5 kilograms, velocity 2 meters per second. That is the momentum of the first object. I didn't put an explicit positive sign, but it's going to the right, so it's positive. Go to the next object. Explicitly, its mass 1.5 kilograms. It's not moving before the collision, so its velocity is 0. All right, I've done the first part. Set it equal to. Now let's set up the next part. The mass of neither car changed. So the first cart, 1.5 kilograms, but I don't know how fast it's going. It's the velocity of the first cart. Go to the next cart, plus 0.5 kilograms, but I don't know how fast it's going. Velocity of the second cart. Now there's a third piece of information that was introduced here. I said the two carts stuck together. The two carts stuck together, what can I say about V1 and V2? They're the same, so I'm just going to recognize they're the same. Now I just got to find out how fast the carts are going. 2 times 1.5 is 3 kilograms meters per second. That equals, can I just add these two up? 1.5 plus 0.5, giving me 2V. So all I got to do is solve for V, and I get 1.5 meters per second. What do you think? Hard? Now, this type of collision where the objects stick together has a name. It's called a perfectly inelastic collision. Almost all collisions are inelastic. The inelastic part just means loses energy. That's all the inelastic part means. Perfectly means sticks together. Okay, that's what the perfectly part indicates, sticks together. So if it says perfectly inelastic, they're telling you the two objects stick together after the collision. Okay, they're saying that to you without saying that to you. All good? How about we try another example? This time we're going to do just a inelastic collision. In an inelastic collision, the two cars don't stick together. But because I want to kind of make this a little bit different, I'm going to say that this car is moving this way at 1 meter per second. By the way, let's handle something real fast before we go on. If I told you this was happening and asked about a collision, what would your response need to be? Why is there no collision? Do we understand that they could do that? There's every reason to believe that they could give you something silly like this. Don't be fooled. The reality of a collision is that there has to be contact. And if one car can't catch the other car, there's no collision. All good? But let's go back to what I had before. Let's make it a collision. 2 meters per second, 1 meter per second. And let's say during the course of this collision, the cars do not stick together. And that after the collision, this car is traveling at 1.6 meters per second. How fast is the green cart going? One of the things I'm hoping you're noticing is that the only way we can find the velocities after a collision is if we're given enough information where there's only one unknown. Are you kind of seeing that? I mean, because this only generates one relationship, a before and after relationship. So you have to have enough information so that there's only one unknown left. But in this case, it'll be 1.5 times 2, that's the first car. And they're both traveling to the right, so they're both positive. So my next one, 0.5 times 1. This has to equal, well, 1.5 times my unknown velocity plus 0.5 times 1.6. Any question about this? Pretty easy so far. My 1.5 times 2 is 3, plus 0.5 equals 1.5v plus 0.5 times 1.6 is 0.8. So 0.8. So 3.5 minus 0.8 is that right? 2.7 equals 1.5v. This stuff really isn't that hard. So I don't know what 2.7 divided by 1.5 is. 1.8. So clearly this car slowed down during the collision while this car sped up during the collision. Now the bell's about to ring, but hear me out. A follow-up question is how much energy was lost. And it's not a hard question. You just do 1/2 mv squared for everything before and after. Right? It's not particularly challenging to think about, but note that that's kind of what I'm going to expect to see you guys do next. All right? We talked about 2 kinds of collisions, perfectly inelastic and inelastic. There is elastic collisions. We'll talk a little bit about those tomorrow. Like that is consider a future problem where we start mixing in stuff from other chapters. And maybe I have something that looks like this. And I'm trying to draw this quickly so I don't waste too much time on it. So let's say that I have a situation that looks like this. I release the green block. Is it probably pretty clear that from here to here, the block's going to accelerate due to the unbalanced force of gravity, and maybe we could use conservation of energy or something like net force to figure out how fast it's going when it makes it to the bottom of the ramp? So during that time, the object's momentum increased due to the force from the earth, right? So now the block has made it to the table and is on the table surface and is moving this direction. And it's going to hit the white block, right? Well, the moment the white block gets hit, it's going to fall off the table and as a projectile. But there's a collision that occurs between the green block and the white block. The collision part of the problem doesn't involve the ramp. and doesn't involve the fall. It involves the moment just before the green block hits the white block and just after the green block hits the white block. That's the collision. But there's lots of stuff around this problem. So when we talk about the collision portion, the part that conserves momentum, that is the instantaneous moment before the collision. So right there, just before contact, and then boom, the instantaneous moment after the collision. Then other forces might take over and might change what the object does. But the collision part is just the moment before and the moment after.